Hi, everyone. It's great to see you here again, joining us this week. Today, we have our very own assistant professor, Soheil Kolouri. He runs the Machine Intelligence and Neural Technologies MINT lab here at Vanderbilt. His research interests are in geometric deep learning, mathematical ML, and computational optimal transport. He's been the PI and co-PI of multiple DARPA programs. And today we're lucky to have him give a talk on kind of an overview of the field of continual machine learning and also introducing some recent works from his own group. So thanks, Soheil.
Yep. Thank you so much, Tyler. Hello, everyone. So again, it's good to be talking at our own machine learning launch seminar. And as Tyler mentioned, today we are going to talk about brain-inspired lifelong learning machines, continual learning. I try to give an overview of the field and then wrap up the talk with some of our recent papers. Okay, so machine learning, as we all know, has become a disruptive technology in many different areas, from healthcare to transportation to energy and retail and banking and so on, right? So for example, in healthcare now we have reliable machine learning techniques for diabetic retinopathy. We have augmented reality microscopes that automatically, you see my mouse? Okay, great. Automatically highlight suspicious parts of histopathology image, for example. And we have good breast cancer detection and so on. And we know that the expectation is very high for the next decade of research in machine learning, but we also need to understand really well, like what are the underlying assumptions in all these machine learning techniques that we are using, and what are the limitations. And hopefully by understanding the limitations a little better, we will have more realistic expectations and we'll be able to focus on more important problems. Okay. So let's the narrative is going to be more or less on healthcare, but this is just a motivation. The problem is not like specific to healthcare, but let's look at machine learning in healthcare, right? So for example, if you're looking at predictive modeling from medical images, classically we had machine learning methods applied to, let's say, classification and regression, segmentation and registration. And those classic methods today are all replaced, I shouldn't say all, but like the majority of them are replaced with deep learning approaches, right? So these deep learning approaches use hierarchical neural networks, and then we can train these end to end from loads and loads of data, and they provide a state-of-the-art results in a lot of these applications, okay? So, I mean, you all are familiar, that has been the theme of a lot of the machine learning seminar talks that we have had in the past few weeks. That deep learning is essentially becoming the most prominent setting or framework in learning from data. Well, this is great, but we also need to acknowledge some of the roadblocks, right? So first, we know that these deep neural networks often require a lot of data, okay? And not only a lot of data, but a lot of labeled data, because their main training regime for these neural networks has been in the supervised learning setting, okay? So if you're doing supervised training, we require a lot of labels, and requiring labels, especially high quality labels, is expensive, right? Because it usually requires expertise and so on. Human hours. So I have worked on this problem in the past as part of a multi-institutional team on a DARPA project called Learning with Less Labels. And so that's something that we are not going to be talking about today. And another roadblock, for example, could be the explainability of these methods, right? If you're only using these neural networks as function approximators, and then we're training these networks on loads and loads of data, we really don't understand what's going on under the hood. We really don't understand why the network is making certain decisions. And it's very important for us to know and be able to explain the decisions of the neural network. the unexplainability leads to a reduction in the trust, and also it hinders scientific discovery from data. So we would really like to have transparent and explainable neural networks. And this is something that I have also worked on in the past, but again, we are not going to be talking about this specific challenge today. So what are we going to talk about? So first, let's just start with the underlying assumption in a lot of machine learning problems. We all hear a lot about advances in AI and machine learning, partly because the field is very hyped currently, but also because there has been great advances in the field, right? So for instance, deep learning was successfully used for detection of diabetic retinopathy, as I said in the first slide. Or it has also been used for successful detection of skin cancer in medical domains. And in these applications, the claim is that these methods perform better or equal to human experts. So this is really exciting. And the human experts in this case are the ophthalmologists and the dermatologists, right? But we should really not forget that the underlying assumption, both in training and evaluation of these machine learning techniques, is that the train and test data are coming from identically distributed, independent and identically distributed samples. So IID samples from a stationary underlying distribution. Okay, so even when we are saying that these methods perform on par with human experts, we should note that the evaluation has been done under the setting, under this IID setting. So both human and machines are essentially evaluated on a test set that are very much similar to what the machine was trained on, right? The distribution is at least the same. So if you're not under this setting, humans' generalization to unseen and out of distribution problems is significantly better than deep learning techniques, right? So still the human generalization to out of distribution remains unchallenged by today's AI and machine learning. Okay, so, but what is wrong with this assumption, this IID assumption? Well, the real world data that we have, the data that's coming from real world is usually highly non-stationary. So it means that the underlying distribution of data constantly drifts. For instance, think of seasonal changes that we are looking at right now. The images look completely different from one another, right? From summer to winter. And there is a huge distribution shift over time. And so if we are training our models, we better account for this distribution change. So going back to the medical applications, these variations in distribution could really pose significant challenges. For instance, there could be variations among imaging devices that we are using, the hardware, the scanners that we are using, or variations at an algorithmic level. For instance, when we are using computational imaging, different algorithms may result in different images with different distributions. Okay, so this is one thing. And also, maybe more naturally, and as we currently know, the diseases could evolve and new variants could constantly emerge, right? That was the case for COVID, the alpha variants, the variant, beta variants, gamma, and so on, Omicron and all that, right? So these new variants can emerge and the distribution of the data could shift as a result of this evolutionary aspect of the disease. Right, so today we are going to really look at what can we do and what are some machine learning techniques that we can use to learn from the non-stationary data, right? Which is different from the classic machine learning approaches. And please stop me and ask questions whenever something is not clear. I don't see the chat, but Tyler can intervene. Okay, so here's the outline of my talk. I start by introducing continual learning and catastrophic forgetting. Then I give some neuroscience inspirations because, I mean, the brain is one continual learner mechanisms that we know. The evolution and biology has come up with such continual learners. So we are going to talk about some inspirations from the brain. And then finally, I'll talk about two of our recent papers on the topic of continual learning, which are inspired by brain mechanisms. So let's start with continual learning. First, where are the shifts, where are the distributional changes that we talked about come from? There are really three different types of distribution shift that we can identify, and there could be a combination of these shifts that are contributing to a distribution shift or the non-stationary nature of our distribution. So here on the top left, you're seeing the original data. So let's say this is the IID samples from the initial distribution that we had. Over time, we can have covariate shift. So what covariate shift is that the distribution, the data distribution, the independent or X's distribution are changing. Okay, so this is simply a change in the distribution of the input data. There can also be label shift. So for example, at a certain time, we might see more of one type of data versus the other. So the balance could be essentially not there. Like it can be like the blue points are more prevalent in this case. But then at last, like there can be concept shift. So this concept shift is when we what we would like to regress on or what we would like to classify itself is changing over time, right? So if you think about predictive modeling in retail, for example, customer behavior is not constant, like it's constantly changing, right? And so what or predictive models need to adapt and become essentially we need to fine tune them to address this problem. Okay, so can't we just train and fine tune our model from one task to another, or like continually fine tune our models on these shifting distributions and get a model that's up to date? Well, that's certainly a solution. And here we are going to look at what will happen if we do that. So consider this these scenarios that we have two tasks. It can be like from going from sunny environment to rainy environment, or going from summer to winter, or whatever two tasks that we would like to have. And given that in the past 2 decades, we've done a fantastic job as a community to come up with better architectures, better optimizers, better tricks to train our neural networks, we are able to train a network that achieves high performance on the first task. And then when the tasks change or this distribution changes, we can still train and learn this model on new data, but this comes at a cost, and the cost is that we start forgetting our performance on the old data. Okay, so we learn the new data, but we forget how to perform on the old data, and this problem is known as catastrophic forgetting. So let's look at an example. Here we are looking at 4 tasks. Each task is a binary classification. So the background color shows the decision boundary of the network. The points are the data that the network is trained on. And this is an easy task, right? Like you can easily train a neural network to separate the 2 classes. And then also for the second task, also for the third task and fourth task. But you can see that every time we are learning the new task, we completely forget where the decision boundary was in the past, right? So this is catastrophic forgetting at its best. Then what we really would like to have is a network that can learn this and eventually learn the overall decision boundary that would have worked for all data. So again, why do we have catastrophic forgetting? Because the main assumption, which is IID samples, is not true any longer. And we know that this is almost never the case. Having IID samples is never the case in the real world applications. So there's a question, could the distribution shift create contradicting input samples? That's a really good question, right? Yes, but it's not clear what we can do if that scenario happens, right? So like fine-tuning your model to resolve contradictions is even a harder challenge that we are not going to be talking about today. But that's a good point. Yes, the distributions can shift, and like what your old or prior knowledge could be obsolete or could become stale over time. So you might need to update it and find things that are not contradicting. But that's a good question. Yeah. So let's look at an example of continual learning in regression this time. So here is a little project that my undergraduate students did last year. It's quite interesting. So we are training, oops, sorry, try to go back. There we go. So we are training the network for a simple nonlinear regression problem. And you see the network is learning to essentially fit a regression curve to the blue points. And then when we train it on the green points, it does that, but it completely forgets where the blue lines were. And here on the right, you're seeing the losses. So the loss for the first task goes down. The loss for the second task is essentially can be anything. But then as soon as you start training on the second task, the loss goes down and the loss for the first task goes up, which tells us that it's catastrophically forgetting. Okay, so this is a super simple problem. It's easily understood what's going on, but is it really the problem for more challenging or more complex situations? And the answer is yes. So let's look at some semantic segmentation results. Here we have driving scenes, and in the middle you see the ground truth. So the task is semantic segmentation. It's essentially we are trying to classify every single pixel in this image. Where is the road? Where are the traffic lanes? Where's the car, and so on. So we can see that we can train a model to solve this problem. And the first task that we have is trained on images from summer. Okay. Now, if we get this model that's trained and is performing really well on the first task and apply it to the winter images, even when it's like this exact same scenario in the winter, we see that there is no generalization. So this is really bad, right? We can't drive in the winter. So we have to fine tune our model in winter. And again, we will be able to do very well in the winter at the cost of forgetting to perform the task in the summer. Okay. So you may also say, why don't we combine data from summer and winter and train the model jointly on these? That's absolutely fine. We can do that. But there is one issue with that framework. And the issue is that as we are learning more and more tasks, this storage, we require more and more storage and more training time. So it's really not a scalable solution. We would like to be able to only fine tune on the current data that we are seeing and accumulate knowledge without having access or without having full access to the previous data. Okay. So while catastrophic forgetting, we've been talking about catastrophic forgetting, and catastrophic forgetting is really considered as the main challenge in continual learning. But continual learning is a multifaceted and very complex problem where overcoming catastrophic forgetting is only a small aspect of this broad problem. So there are other aspects that are equally or even more important. And we can, for example, talk about obtaining positive forward transfer between tasks. So learning one task should help us learn the next task with better accuracy, or rapid adaptation and sample efficiency in learning new tasks. Learning old tasks should help us learn new tasks faster. And also resource awareness. We would like to have constant computational and memory resources so we can implement these on our machines and deploy them in real world. And lastly, we would like to be able to perform continual learning on a continuum of tasks, not just discrete tasks, summer versus winter. We would like to have a continuum of change, drift in our distributions, and learn from these distributions. Okay, so these are some of the things that we would really like to have. And now I'm going to talk about the brain and discuss some of the known mechanisms that the brain uses to address continual learning. Okay. So we know that the brain is the best example of a continual learner that we have. And the idea here is that can we use inspirations from this organism, the brain, to design algorithms and to design new algorithms that are kind of like independent or complementary to the mathematical and logic-based methods that we often follow to design new algorithms in ML and AI. So there is this fantastic paper in 2017 from Demis Hassabis at DeepMind, he talks about neuroscience-inspired artificial intelligence. And there are some very interesting points there. And so one of the points is we shouldn't be slaves to the biology, in the sense that we don't want to like exactly replicate biology in AI. But we don't want to go at the molecular level and do this. But we would really like to understand the mechanisms and treat them as algorithms that the brain is using, and try to bring those algorithms in the AI and mathematically formalize them and provide the similar capability for our neural networks that the brain has, without replicating every single thing in the brain, right? So that's the idea, and this is how neuroscience can help advance AI. But there's also like the arrow can go the other way. Like the advances in AI can also help neuroscience by finding shared themes that may be really key for understanding the brain better, as well as designing better algorithms in our neural networks. So we recently published this paper on the biological underpinnings of continual learning at Nature Machine Intelligence. This was part of the effort by the DARPA Lifelong Learning Machines team. And in that paper, we identified some key characteristics of a continual learner. So for example, we would like to have transfer and adaptation, as we talked about. We would like to be able to overcome catastrophic forgetting. We would like to exploit task similarities. So if two tasks are similar, we should be able to rapidly adapt and learn a new task that's similar to the old tasks that we had. We would like to be able to perform in a continuum of tasks in a task agnostic manner. And also we would like to be able to have resource efficiency for sustainability, right? So if we think about these as like 5 pillars, and there can be more, but we're going to focus on these 5 for now, then we can associate some of the mechanisms in the brain that enable these characteristics. So for example, we can talk about neurogenesis, episodic replay, metaplasticity, neuromodulation, context-dependent perception and gating, and so on. And we see that the brain is really using all these different mechanisms to address these different challenges in continual learning, right? In particular, for overcoming catastrophic forgetting, like many of these mechanisms are contributing to this, this aspect of continual learning. So I'm going to briefly talk about these 4 mechanisms: neurogenesis, episodic replay, metaplasticity, and neuromodulation, and what they are. I'm not a neuroscientist by training, so I'll try to keep this part of the talk at a high level, but I hope that the ideas will be conveyed accurately. Okay, so metaplasticity in biological neural networks is referred to the way that the neurons, the dendrites in the neurons, become more or less plastic over time. And this more or less plasticity over time is going to allow us to store some memories and forget other things. So there are these little bumps on the dendrites. These are called the dendritic spines. And we know that as a function of learning, these dendritic spines are going to dynamically change their morphology. So they're going to become thicker or thinner over time. And the density of these dendritic spines is going to change, okay? And so the ones that, the dendrites that have dendritic spines that are stably maintained are actually going to be less plastic, and they are going to store memories for us at a very high level, right? And they are associated with lifelong memories, okay? So, but if we think about our unlike these biological neurons, and if you think about our artificial neural networks, in artificial neural networks, we have uniform plasticity. And what we mean by that is that every parameter is in a neural network is as important as another parameter. So, and they can change this in the same manner. Okay, so this synaptic plasticity regulation in the brain has really inspired many approaches on selective plasticity for artificial neural networks. And we are going to be talking about some of these approaches in upcoming slides. Another prominent mechanism is the episodic memory replay, or essentially, which is very much related to the complementary learning systems in the brain. So the complementary learning systems in the brain refers to the play between hippocampus and neurocortex, where like the episodic memory, very short-term memory, and fast learning is happening in the hippocampus, and then slow learning of a structured knowledge is happening by replaying information from the episodic memory or from hippocampus into neurocortex. So we obtain things very fast. We hold them in this like fast memory, and then during rest time and during down times, what will happen is that there is going to be replay from the hippocampus into neurocortex, and the longer term and slow learning is going to happen in the neurocortex as a function of that. So modern machine learning techniques rely on experience replay approaches in continual learning. And this is also very prominent in the reinforcement learning field, where continual learning plays an important role. So having these short-term memories, memory buffers that are episodic, and we are going to replay from them to train our neural networks and have more structured knowledge, is a common practice in AI as well. So another mechanism that we talked about is neuromodulation, and neuromodulation refers to the neurotransmitters in the brain and how they affect the neural activations or neural firing in the brain. So we can think about the neurons as having presynaptic activations, and then like we have postsynaptic activations between the two neurons. And even for the same presynaptic activations, the postsynaptic activations could be different and could be context dependent, right? So for the same inputs, the output could be different. This is not a function necessarily, right? And why is it different, and how is this? Where is this difference coming from? This difference is usually coming from the modulatory signal and through neurotransmitters. So again, for the same inputs, a neuron can behave very differently, conditioned on existence of presence of some neurotransmitters in the brain. And these neurotransmitters, what they're doing is they're really inhibiting or exciting the activations in the brain. So making a neuron more or less likely to fire, okay? And we are aware of many of these, like serotonin, acetylcholine, like dopamine, and so on, right? So these neuromodulatory signals really change the dynamics of neural activations, and they have inspired a lot of different applications in artificial neural networks, specifically for continual learning. And lastly, and I'm not going to be talking in depth about this one, this is neurogenesis. And what neurogenesis is that our brain still, even adult brains, still create neurons in certain regions of the brain, in dentate gyrus. And like this new neuron generation essentially plays an important role in maintaining memory and memory formation, okay? And similar ideas have been used in artificial neural networks, where we expand neural architecture to learn new tasks, right? So the network can progressively grow and become bigger to be able to solve more and more tasks. Okay, but what is the landscape of continual machine learning? So today we have like maybe three main thrusts, actually four, and these address the problem of continual learning, or we should say they address the problem of overcoming catastrophic forgetting, or or the catastrophic forgetting problem. And these methods are replay-based methods, which are really motivated by experience replay, regularization-based methods, which are motivated by metaplasticity approaches, and then parameter isolation methods, which is a combination of neuromodulation and neurogenesis approaches. And one of our previous speakers from DeepMind, Mehrdad, talked also about the role of architecture and training regimes for catastrophic forgetting. But I don't want to bore you with the details of these methods, but I really want to understand, like, what are the broad mechanisms used here? So we can think about these mechanisms as change in the dynamics of synaptic weight updates, or how we are updating our neural networks, change in dynamics of activations, neural activations, through, for example, neuromodulation, and then dynamic changes in the architecture. So we would like to essentially add new neurons, or maybe mask some neurons, and so on. So going back to this figure, we can, as mentioned before, we can see that the brain uses many of these mechanisms together to be able to overcome catastrophic forgetting. And this is while a lot of the approaches that we saw in the previous slide, for example, use one of these mechanisms, okay? So we really believe that this could serve as a roadmap for designing the next generation of bio-inspired continual learning algorithms that combine these different brain-inspired mechanisms into an algorithm that can solve continual learning better than each individual mechanism, okay? So we ourselves, and my lab and myself in the past have published on these continual learning approaches a lot. And we have also focused on single mechanisms like metaplasticity or neuromodulation or replay-based methods. But really the breakthroughs should come as a combination of these methods. And there is a recent movement towards, from recent publications in the field, that they use more than one of these mechanisms. So several of these mechanisms are used to overcome catastrophic forgetting. So today we are going to talk about one approach based on metaplasticity, and then one approach that combines metaplasticity and neuromodulation. So let's start with the metaplasticity approach. This is a work jointly done with Nick Ketz, Andrew Soltaggio, and Pravin Pillai. It's called Slice-Kramer Synaptic Consolidation for Preserving Deeply Learned Representations. Excuse me. This is an iClear 2020 paper. So let's motivate the problem. We are going to look at one of the core, one of the benchmark problems in continual machine learning, which is called permuted MNIST, okay? So in permuted MNIST, your first task is usually MNIST dataset, which is the handwritten digit recognition problem. And then the following tasks are a permuted version of these digits. So these are not human understandable, but they are essentially equivalent from a perspective of a machine, because it's just a permutation of just a permutation applied on the input. Okay. So these problems are as difficult as each other, and we are going to use a multi-layer perceptron to solve this problem. First, we are going to learn task one. We go from the 784 dimensional input to a 2-dimensional embedding, and then classify our samples from on this 2-dimensional embedding. So if so, I'm going to use phi of theta as my function that embeds my inputs. And if I look at the distribution of my input images in this 2-dimensional space after training on MNIST task, I'm going to see that the different digits are going to be associated with different parts of this 2-dimensional space. Okay, so now I have a discriminant embedding space for MNIST after training my phi on the MNIST dataset. But of course, if I apply the permuted MNIST, send images from permuted MNIST in my network, I'm just going to get garbage, right? This is not a discriminant network for my second problem. But if I fine tune my model on the second problem, I'm going to get a discriminant embedding for that and lose my discrimination for the first problem, right? So this is catastrophic forgetting that we have talked about. So what we really would like to have is a method that we can fine tune on the new task while preserving the distribution of the old task, okay? So let's see how metaplasticity approaches work. So metaplasticity approaches try to solve this problem and essentially give us this nice distribution preservation by saying that not all synapses or parameters in your network are equally important. So after you learn one task, let's say task 1, you go and you consolidate the knowledge. And what this consolidation is that you estimate importance values for the parameters that you have in your neural networks. Okay. So now some of these synapses and some of these parameters are going to be more important for task 1 than the others. And when we are learning task B, we would like to regularize or penalize our network for changing the parameters that are important. So we have estimated these importance values. We show them with omega I. And then we say that if something is important, if omega I is high, you can't have a large change on that parameter. Okay. So we can really think about a spring system where if this omega is high, you can think about a thick spring. And if this omega is low, you can think about a very thin, weak spring. And if this spring is thick, it means that you can't move this spring too much. So your task is trying to pull it in one direction, but the spring is too thick and it won't let the task to pull it. Okay. And with that, we will be able to preserve or representations for all tasks. Now the question is, how do we calculate these importance values? Okay. So let's look at this problem. Again, we have task A, and then we are learning task B. So we are going to show the network after training task A as phi with parameters theta star A. Okay, so phi at theta star A push of PA is the distribution of task A after learning task A in the embedding space. Then we would like this this distribution essentially not to change over time. So we would like to be able to look at the distribution of the samples from task A under the updated model. So this is the model after training on task B. And we would like the difference between these two distributions to be small. So this D is a difference between the two distributions, which is telling us that the difference between these two distributions must be small. Of course, this relies on the distribution samples from task A, but bear with me, and we'll see that this will vanish. So here we need two assumptions. First, if we assume that the delta theta, which is the difference between theta B and theta star A, if this is a small, then we can use a second order Taylor expansion of our distance, D, and we can rewrite this whole optimization problem as a quadratic penalization. So it's essentially going to be our loss for task B plus lambda, which is our coefficient, regularization coefficient, delta theta transpose omega A, delta theta. This omega A is the Hessian matrix for our distance. Okay. Of course, this Hessian matrix is the number of parameters by number of parameters. So it's like a gigantic matrix. And we would not like to have that. A neural network can have many, many parameters, and we don't like the idea of having this gigantic matrix. So we can make another assumption, and this is usually not a very good assumption at all. And we have papers showing that. And so we can essentially, if we assume that this is a diagonal matrix, we can write it as a summation over the diagonal values times delta theta I squared. Now we see that this is exactly in the form that we had in the previous slide, where there is an importance applied times the amount of changes in a parameter that we have here, right? So how we calculate and how do we estimate this? We just simply need to calculate this distance and look at the second order Taylor expansion of that to find our importance parameters. And again, there are two assumptions under this framework. Okay, so what is a good dissimilarity measure, D? Well, we can use, we can look at the elastic weight consolidation and memory aware synapses. These are two prominent frameworks in the literature. And what they do is they look at the expected value of a sample difference between our outputs of the model B and our output of model A, right? So this is a sample-based distance, and we are looking at the expected value of the difference between the samples. So we observed that there is one issue with this framework, and the issue is that I can really have distributions that do not change over time. So let's say this is showing a distribution of my samples after learning task A, distribution of my samples after learning task B. And we see that the samples are moving around. So they're actually flipped in this case. But the distributions haven't changed. So because the distributions haven't changed, there is no catastrophic forgetting happening here. But both of these methods, because they are using a distance that's sample-based, they're going to penalize such changes. So what does this mean? This means that these, if you're using a sample-based regularization, we are going to essentially have overestimation of importance parameters. So this is an okay change for catastrophic forgetting, but the penalize this regularization term doesn't let us do it. So what else can we do? Instead of using a sample-based difference, we can look at a distribution-based difference. And if we look at a distribution-based difference, the distance between these two is essentially minimal. It's 0 in this case. And what can we use for that distribution difference? There are like many options, like Wasserstein distances, slice-Kramer distances, max-mean discrepancy, and so on. And in our iClear paper, we specifically used the slice-Kramer distance because it led to a very nice algorithm for overcoming catastrophic forgetting. And going back to the permuted MNIST problem on 10 tasks, we tested our method, this slice, essentially the distribution-based regularization based on the slice-Kramer distance compared to the EWC and MAS. And we see that if we don't do anything to our neural network, it's going to catastrophically forget, of course. So this is catastrophic forgetting happening here. And if we learn with these different mechanisms for continual learning, we saw that a distribution-based regularization leads to significantly better performance compared to the alternatives. And going back to our semantic segmentation problem, this was the case where we didn't get generalization. Now, if we train or fine-tune our network on task B with this slice-Kramer preservation, we see that we are able to learn the new task at the same time preserving our knowledge or performance on the previous task. So without using any data from previous tasks, we are able to fine-tune the model to perform well on both. And here are some more quantitative results. We show that we have less catastrophic forgetting and also better utilization of the network capacity. And this is all with that simple observation that a distribution-based regularization could work better than a sample-based regularization. And that's really it. Some more qualitative results. Okay, given that I'm running out of time, I would like to just speed up a little bit and talk about the last last paper, which combines the ideas of metaplasticity and neuromodulation. This is called the sparsity and heterogeneous dropout for continual learning in the knowledge space of neural activations. It's a joint work with my students Ali and Parsa at UC Davis, Vova Braverman at Johns Hopkins University, and Hamed Pirsiavash at UC Davis. So we just talked about metaplasticity approaches, and we saw that the overall framework gives us something like that. So we have a loss for the task plus some regularization that is telling us don't change important parameters. If we calculate the gradient of this loss function, we see that the gradient of the task is here, plus this additional gradient, which is the gradient of a regularizer. So this additional gradient is essentially changing our trajectory. The gradient descent wants to take us in one direction, and this addition is going to essentially add and change the trajectory into another direction, which is going to help us end up in a place that's better for solving both tasks. Okay. So one way to, of course, change the trajectory is by this addition, but there is another way that we can change the trajectory, and that's a projection-based method. So we can simply say, hey, get the gradient that you had for task B, and then project it onto a subspace that ensures that no interference with prior tasks is going to happen there. Okay. So these are two different ways that we can change the dynamics of our synaptic updates. And this latter mechanism has become very popular in the field, and it's very successful. One of the state-of-the-art methods currently is this projection-based continual learning. So let's look at the intuition. Let's say we have a neural network with simple multi-layer perceptron that receives data from task A. We are showing XA of I as the ith sample of our task. We have WA1 as our weight of this first layer, weight of the second layer, and weight of the third layer. And the subscript A tells us that these are optimized for task A. Okay. And this F is the activation. So for example, you're using ReLU. So linear followed by non-linearity, linear followed by non-linearity, and so on. Okay. So if we want to guarantee performance preservation, what we really need is that the weights of task B after learning task B applied to or samples from task A should be equal to the weights of task A. So the best parameters for task A times the same samples, right? Okay, so like how can we do this? Of course, we can always write this WB as WA plus some delta W. So this is where we were before we trained on task B, and this is the update that we gain by fine-tuning our model on task B. And then if we just simply expand this, we see that WAL appears here, and then we have this delta WX showing up here. Okay. And if we really want this equality to hold, then we need this delta WA, delta W times XA to be 0. Okay. So if our updates are in a way that's the inner product of our updates and or data from previous tasks at each layer of the neural network is 0, then we won't have any forgetting. We're guaranteed not to have any forgetting. So what are the implications? This implies that, and I promise I'll be done in 5 minutes. So this implies that we would really like to project our gradient of task B into the knowledge space of our activations for the previous task. So if we look at the subspace, that's the span of all neural activations for the previous task, what we really want to do is to project this gradient into the knowledge space. And if we do that, we guarantee that this is 0, and the representations, the activations have not changed as a function of training on the new task. So this is the core idea behind gradient projection memory, which was an ICLR 2021 paper. Okay, so if we go with this framework, we need to immediately look at the inherent assumptions. Again, the inherent assumptions behind any approach. So this approach assumes that the subspace, the activation subspace for every layer is low rank. Why? Because if it's not low rank and we are doing a projection onto the knowledge space, this projection is going to ruin all the information that's in this gradient. So in the worst case, our subspace can be full rank, and we are essentially projecting this into a empty space, which is 0, and we are not going to be able to learn new tasks. Okay, so this is one major assumption here. And then the other assumption is that we really are in a scenario that we don't care about backward transfer, because by definition, if we are updating our network in the knowledge space, we are not going to change our previous representation. So our performance on previous tasks are going to be untouched. They are not going to become worse, or they are not going to become better. Okay, so there is no backward transfer. And we don't address this problem, but I just want to point out that this is a known issue, and there are very interesting recent work in this direction to allow for backward transfer for projection-based methods. And one such paper is Trust Region Gradient Projection for Continual Learning in ICLR 2022. Okay, so we are going to focus on the first part. How do we ensure low-rank activation subspaces? So we have been studying a lot of work on sparsity. We can have sparsity neural networks in the parameters or in the synapses, or we can have a sparsity in neural activations. In particular, there has been a lot of work from Numenta on this topic, and we have some we have some collaborations with them. So we were very familiar with these approaches, and we started asking ourselves, can we use a sparsity to enforce low rank activation subspaces? And in theory, low rank sparsity should not lead to, does not necessarily lead to low rank activation subspaces. But in practice, we see that actually, if we use a sparsity, we are going to allow for low rank subspaces. So what we use here is the K-winner activation. And for those of you who are not familiar with this, think about ReLU. ReLU is essentially a max of 0 and your activation. So this will zero out everything that's below 0. And here the K-winner does something a little different, and it looks at all the activations in one layer, and it just picks the top K ones and then zeroes out everything else. So it's still a nonlinear activation, but it's not just independently applied to the neurons, it's applied to a group of neurons. Okay. So long story short, we show that this sparsity leads to low dimensional subspaces. If we train a network on, let's say, MNIST with this K sparsity, we are going to get a network that has low dimensional activation subspaces. So because of time, I'm not going to cover that. And then one last thing that we looked at was, again, neuro-inspired, and in brain, we know that non-overlapping neural activations are helpful for continual learning. So we enforce our network to drop out the neurons that are more active. So drop out the neurons that are frequently active, and they were frequently active for the previous tasks, and use the network, use the neurons that are less, that have been less activated for previous tasks. And how we do it is essentially we do a heterogeneous dropout. We estimate how frequent each neuron has been in its lifetime on all tasks. And we simply define a probability of dropout on that. If the frequency was high, if it was activated a lot, then drop it. It should be more likely to drop it. Okay. So again, the entire architecture, if we put everything together, has K-winner activation as a sparse neural activation. We have heterogeneous dropout, and we have this gradient projection mechanism for continual learning. And when we put all of these together, we are able to overcome catastrophic forgetting much better than the simple gradient projection based methods. And we have ablation studies that show the effectiveness of the heterogeneous dropout that we talked about. If we don't use it, we get the blue lines. If we use it, we get the orange bars here, which shows that there is a consistent benefit in using this heterogeneous dropout. And this is permuted MNIST on 50 tasks, by the way, which is kind of considered a lot of tasks in continual learning. And last is we define this continual Swiss roll experiment. This is 50 different tasks. Each task is a binary classification. And you can see that we start from task 1, and you have to essentially learn all the tasks, but you only see the data from the new task at each step. And if you do this, learn this task with our method versus GPM, you see a significant difference in case that GPM actually does not maintain the performance at all. Well, if you do joint training on everything, like, of course, you get very nice decision boundaries, and we see that our decision boundaries are significantly closer to the ground truth decision boundary or the joint training, while we are seeing the data sequentially. And in the bottom, you see the progression of this decision boundary as a function of number of task scenes. So somewhere around here, you see that the GPM starts forgetting everything, and essentially the decision boundary is fine here, fine here, fine here, boom, like it doesn't perform well after that. Well, we are able to maintain very well, a very good performance throughout the 50 tasks. So yeah, with that, I would like to thank my students, my collaborators, and DARPA for funding on both lifelong learning machines and shared experience lifelong learning. Yeah, I'll be happy to take any questions from you.
Well, thanks. I guess those of you willing to kind of unmute and you know, kind of clap, or at least virtually, I guess some of you doing. Yeah, so open for any questions, either in the chat or preferred if you can unmute yourself. Okay, maybe I can start with one. So the one thing that I was curious about is perhaps the relationship between the model complexity and then the number of tasks, or these kinds of the number of distribution shifts or changes, especially in relation to something like these regularization-based approaches. Is that perhaps why in the second paper, when you showed getting more and more tasks, this kind of change in that curve?
Right. Yes. So the complexity of your model is a very important confound, right? So the larger number of parameters that you have, and the wider your neural network is in these cases, the less forgetting you're going to have, and you will be able to handle more tasks without forgetting, right? But the real problem comes in, like, are we utilizing the capacity of the network in an efficient manner, right? Because, like, given that the capacity is fixed, what algorithm should we use to ensure that we can pack more and more tasks into the same network? And so this is really the business that we are in, right? So we would like to find algorithms that maximizes or the utilization of the exact capacity that the network has, right? So yes, you can always overcome catastrophic forgetting better with larger networks, but for a given fixed architecture, like, what would be the best algorithm for overcoming catastrophic forgetting?
Okay, a follow-up would be, so then if kind of empirically, if you know that your problem is inherently going to have these changes over time, would we want to somewhat initialize with maybe a slightly more complex model than necessary for the initial problem, anticipating this kind of continual learning setting?
Absolutely, right. So yeah, I mean, if we can afford larger networks, that's absolutely that's a great idea, right? Also, recent studies show that, for example, self-supervised learning on a gigantic set of data as a pre-training will make a better continual learner. So whatever task that you have, so long as it's relevant to your self-supervised pre-training, if you have used pre-training on a gigantic network on a lot of data, and then you are going to have a better initialization for continual learning, right, on the subsequent tasks that you have, right? Even when those subsequent tasks are, let's say, supervised classification. But so initialization is important. Model complexity is certainly important. And again, like we saw, like from Mehrdad's talk that training regime optimizers and things like that also matter a lot in continual learning.
Okay, thanks. Does anyone else have any questions? Oh, looks like one just came to the chat.
Yeah, I think Lance saying, pardon me for my linear algebra, why is rank related to this subspace? Okay, so what we have over here, let me go to, right. So what we have over here is saying that the inner product, like, this is the delta W is a matrix. The matrix vector multiplication that we have here is going to be 0, right? Regardless of what layer we choose and what I we choose, right? So really, if I think about this as a vectorized version, this is simply a linear inner product between the delta W and XA, right? Okay. So now, what's happening here? And I mean, of course, a repetition of X. What's happening here is that we would really like this to be 0 for all XAs. And what we can do is say that we are going to go and learn a subspace that is the span of all those XAs. So any vector, any XA now lives in this subspace. Okay. So now I want the inner product of my delta W and any of these XAs here to be 0, right? So then, like that means that it needs to be in the null space of this subspace, right? So that's the intuition. If it is in the null space, it's essentially orthogonal to that subspace, and this inner product is going to be 0. So that's one. How is using the wolf activated neurons linked to the neuromodulation? Oh, that's perfect, right? So we talked about neuromodulation as a way of changing the dynamics of activation, right? So if we don't have neuromodulation, this neuron is going to fire. Okay. Now we are going to say, hey, I'm going to take some more information into account and see whether this neuron has been activated in the past or not. And if it has significantly been activated in the past, although I should activate it again, but now I'm going to drop it. I'm not going to let it be activated. So I'm essentially down modulating that neuron's activation. What is affecting this down modulation? This additional information that is coming from the frequency of previous activations. And because we are changing the dynamics of activation, this is very much similar to the ideas of having neurotransmitters that are down modulating or up modulating neural activations. Okay. Thank you. Yes. Awesome. Great. So we are slightly over. Thank you everyone for coming, and thank you Tyler for questions. Thank you Lance. Yeah.
Thanks. And congratulations to you and your students on the recent works.
Thank you. Appreciate it.
See you.
See you.
See you.